Hello, welcome back to the shop. So today we're going to take a look at the idea of doing a project. So anytime you start on a project, you have an idea, you want to get your idea down on paper so that you can start critiquing it and building it and doing whatever with it. So this is an idea started out. What I wanted to build was a portable inverter. I know you can buy these things, but I kind of have a specialty use in mind for my own thing. So what we want to do is we want to look at the basics of what we need. We need batteries. We need a way to charge the batteries. Need a way to get power to the charger. Isolation of the charger. Need the inverter to create the 120 volt for our power. And we need to be able to turn on the 120 volt. Again, isolation, you don't have to do that, but it's just something I wanted to do. You need a way to turn the inverter on. You need a way to switch the inverter on. That would turn on and off your relays. Now what I wanted was I wanted a remote control, so I don't have to be standing at my power inverter to turn it on and off. So that's what this does. And why not put USB charge on it? So when you get down to all that, you start getting some components together. So let's just look up at the top here. Need power in. So we will identify a casement at some point here, but there's our power in. This would mount on our case, and this would be our top component. Here I have an isolation switch which I later delete, but we need a charger. I identified this charger that I liked. I've used it with other projects, so I wanted to continue with something that I liked, so I got one of these. Next we have our battery, arguably the most important part of the thing. And what I did was I decided to get a lithium iron phosphate battery. I originally got lead acids, and I decided not to go with the lead acids because of weight. I figured this would be a great experiment for the weight. This is 30 amp hours, and in the same casement the lead acids are 18. So we just about double our capacity on this project using these. They claim they have a high cycle time, all that other stuff, lighter weight, stronger charge and discharge ability, and they do have a battery management system built into the top here. So I thought this would be a great project to play around with. Battery management system being very important so that the cells don't get overcharged and over discharged. So important step there. The inverter, I don't want to go too big for the inverter. So I got this. It's a 500 watt inverter. It's an all metal casement. I thought this would be important for heat sinking because we're going to be putting it in a box. Some inverters are plastic and whatnot, so we'll take another look at some of the what we'll end up doing to try and cool this thing. So, and we don't have astronomical currents as well. You can see this is actually 49 amps, and we do our 80% of that. We end up around 70 amp fuse. Should be like 62, but we ended up with 70. Then the inverter needs to get its power out, so we got these regular flanged outlets. For switching, I went with these 19 millimeter 5 amp rated screw terminal maintained switches. You can see that's maintaining, so you push it on, push it off. I got 5 of these. Okay, so we got our switches, control relays. I am a little torn still. I have 2 options for the inverter. I need something somewhat beefy. This is rated 80 amps. It's a regular style contactor type thing. You can see it's 2-pole. I don't really need 2-pole. This is single pole, double throw, and this is 2-pole double throw. You can see the double throw there, normally closed, normally open. And this is basically the same thing, but this is rated 250 amps. So this is smaller, rated for higher current. I don't know that I trust 250 amps on it, but I think this is the route I'm going to go, just to give it a go, see how it works. So we have the relay to turn on and off the inverter, and then we have some typical ice cube relays here, 120 volt, contact rated, and 12 volt coils, just DIN rail mount. These we're going to put on the on these outlets here, so that'll be controlled by a switch or our remote. Which brings us to the next thing, our remote. Remote being desirable for me, this is a little battery operated remote, and that operates this relay block. This gets power to it, and then it's got a receiver in it, and this is your transmitter. And when you push on, it turns it on, and when you push off, it turns it off, theoretically anyway. So that would allow us the ability to not be standing right with this thing to turn it on and off. So that's just a feature that I wanted for myself, and that's part of the reason why I'm building one of these. Plus, building things is fun. So there's our remote. Next, USB charge and voltmeter. Well, who doesn't want to have USB charge on everything? And the inside of this is a digital display telling you how much voltage you have. So, and this has got a little window. There you go. It always shows the voltmeter, and when you open it up, you can use the USB charge. So that's a handy feature. So that's the first iteration. That led to the second version, which we started cleaning the drawing up a little bit here now. We're showing the 2 batteries. We eliminated the switch for the outlet here. We really didn't need it because either it's plugged in and the power goes to the charger, or it's not. So the switch up there really didn't gain us anything. This switch is the important switch, because these chargers, they do have a little bit of a parasitic draw on your batteries, because it's always looking for a reference voltage in order to know that to turn the charger on and off. So isolating the charger on the load side with 12 volt is a very good idea. And then did some calculations and came up with fuse sizes. Got a 5 amp fuse to charge into the batteries. All this is starting to evolve here now. That's like I say, you start cleaning up your drawing. Here we have, at this point I just threw 80 amp fuses on it because I didn't calculate anything yet. Feeding that control relay, this control relay. So now we start getting some other components involved with this thing. We need some fuse blocks, and I opted to get one of these, and these are kind of interesting, I should say. They take your regular automobile style fuses. I think it's AGC, I forget though. Here's your negative terminations and positive termination. It runs a bus inside of here, and the other side of the fuse terminates here. One nice thing is they have a reference voltage on here, so if a fuse blows, this light will light up and it'll tell you which one went. I don't really need 12, but I have options for future if I wish to extend this thing. As far as the higher current fuse, I got one of these, which is a mini fuse size. It's just a main fuse block. This is being fed on this side, and then there's 2 fuses right here, and that will be this fuse and the fuse that feeds our other fuse block. So that ends up being these 2 fuses, which in the next version we'll see which currents those become. So we got the addition of fuse blocks, And we have also got the addition of a 12-volt outlet. So that's another thing that's not, it's just a different thing that I wanted in my purpose for this thing. So I have a 12-volt outlet, 120-volt outlet, 5-volt outlet. I got a whole bunch of stuff going on here. So kind of handy. Now, this is an enclosed case. Got thinking a little bit more about it, did a little bit more refining. Ended up with some fans to try and circulate air through the casement. And that's the biggest addition in this version. And for fans, what I got was 40mm fans with grills. So we're going to cut these into our casement. Just drill a hole the size of this and bolt it all together. Should be reasonably decent. Not really watertight, but hey, you got to have some airflow. So that's the biggest change here. And that led to the final version here. With contacts and relays and stuff, you end up shortening your lifespan with DC with loads and opening contacts under loads. So what we ended up doing was getting a bunch of diodes that we're going to put across anything that's a load on this thing. So we got these smaller diodes here that we're going to use for like the relay coils, all of that stuff, all of the smaller stuff. And for the larger things like the inverter, I got this 100 amp rated diode, and we'll obviously have to mount this on a heatsink. And we got the 50 amp diode for our 12-volt outlet here. So this one I probably didn't need to go to, but you never know when things get turned on and off, so we got one just to protect those contacts. So now we have diodes for this whole thing. We also have a relay here for the receptacle, and we went with a 40 amp rated, just a regular Bosch style relay. Wouldn't trust 40 amps on this. It's maybe 12 gauge wire, but we're running at 20 amps, so we should be fine here. Contacts are more robust theoretically than what we need, so that gets us that control relay. And I added 2 additional fans just because I went smaller with the fans to try and fit things in, and I was able to get them in more than I thought I could. So I was able to go bigger there. So that was nice. So there we have all that stuff. We added everything in. We have ourselves a loose drawing to work off of. We got our fuse sizes in everywhere. Now we're at a 70 and a 50. Probably hard to see. And we got fuse sizes all down through here. So now we have a drawing together for how we're going to do this project. Now we need to start looking at, we have a lot of our material here, and now we need to start looking at how we're going to design the actual project and make everything work out well. Okay, so casement placement and everything. One of the advantages to these lithium iron phosphate batteries too is you can flip them around every which way. But as far as our casement goes, we're using a Milwaukee PACKOUT, and that's another reason why I wanted to build this, because I liked the idea of using a PACKOUT. I can store it easily, and I can take it out and what have you. So now when we start laying the pieces of the puzzle out here, we just need to get some loose measurements, and bear with me on the camera angles. I can't get the camera back too far in my current situation, but I'm just centering this stuff up a little bit. Okay, so we're pretty close to center there, and I think I want to have the batteries towards the back of the casement, and that should allow me enough room to get these fans mounted at this spot, and that would allow us to have airflow through here. Now, one thing that we have to do is we actually have to fire up this inverter and see which direction the airflow in this inverter is going. Inverter has a fan as well, and we want to make sure our airflow matches the inverter's airflow. If the inverter wants the air to go this way, we don't want to be sending our air this way. It'll be fighting each other. Alright, so we have our inverter temporarily hooked up here with alligator clamps to the battery. And one way to tell is you can look in here at the fan blades, which you can't really see, but you want to see which direction the fan turns. It turns clockwise, and the pitch of the blade is facing out here towards the bottom of the blade. So that should mean that it wants to force air outward towards us. And you can kind of test that by just holding a bag over this. And if it wants to suck it fast while it's running, it's intake. And if it wants to kind of blow it out, it's outtake. So it's not sucking it fast. So that means this is outtake. So what that means for us is we want our DC connection. We're going to try and divide AC and DC in our cabinet as much as we can. So we're going to mount this like that, which means our airflow is that way. The AC side here being the intake, and the DC side being the out. So we're going to mount just like that. Airflow goes that way. Now we want to do the same thing with this fan. You can see I already have it running, but we want to see if it wants to suck. So here you can, let me get in frame. There we have the wants to suck the bag right into the fan, and here we're blowing it away. So we know discharge of this is on the label side, and intake is on the non-label side. So that's going to be important when we mount these in our cabinet. Two are going to have to be mounted one way, the other two are going to have to be mounted the other way. And they'll have to match the airflow of this. So now we know in our container, our pack out, we're going to have two fans mounted this way, discharge being on the label side, this being our intake side, this being our outtake side, and then two fans mounted this way. So what we'll get is a nice airflow through our cabinet around the batteries. So looking at this, we have just enough room to fit these right like this in the corner of this pack out. So what we want to do is we want to measure what size hole we have here and lay this out in the pack out, and then see if there's any bracing or anything that we're going to be drilling into on the back side or anything like that, and then that will allow us to get these mounted in here, two here and two over here, and the two over here are going to be facing the opposite direction. I'd like to go over design and really what goes into some of it. I mean, I didn't have any drawings for how this thing would look when we started this project. We just kind of had an idea. So we'll roll through some of the evolution of this project as it went through. So got the idea, the basic idea down on paper. And that's what you see here. It's the main integral parts. We have our batteries, have our inverter, have a charger, have our outlets for the inverter. We have a way to get power to the charger. At this point we had a switch in there. And then, you know, we have a means of disconnecting. We have a means of turning on the inverter. We have a means of turning on these two outlets. And we have a remote control and our USB meter. So that's our first version of it. Now when we get to the second version, we start to clean it up a little bit. Add a few things. At this point, we realized that this was kind of redundant. We didn't need it. If the plug's unplugged, there's no power, so we didn't need to isolate that. We cleaned that up. Now we've labeled our batteries, and that we've also added some more fusing. There was really no fuses at all in the first version. You can see that. Now we've started to clean it up. We've made it more functional. We've added fuses, and we've also added the 12-volt receptacle here. So we did that. Now we're just going to go through, and you can see what do we do here? We just kind of... Oh, okay. So then we realized that we needed to add fans for the inverter to help keep it cool. Added another fuse there. There's our fans. Started with 2 fans. Then at this point, we were looking at it a little bit closer, and we figured we could fit 4 fans in, 2 on each side, and that would equal the larger fan, or exceed the larger fan on the inverter. The point was to actually exceed it. The inverter had a slightly bigger fan, so to go with these, that forces additional air through that's not going through the inverter. But that's so there's that. We got all the fans in, and then now we went through and we realized that we should put some diodes in to protect the switches. So that's what we've got here. We started adding some diodes in the circuits to protect things. Just clean that up a little bit more. Here was some scribblings. We were going to omit a few things and change things around, and that didn't work out. And then here's the final drawing. Now we've added that additional 12-volt receptacle. That also has a diode. Here's our 20 amp receptacle diode. So you can see here how just things really change from beginning to end. It's not quite the same thing, and there's nothing wrong with that. I mean, you're really just, when you come up with something, now there's probably more elegant ways I could have done some of this, but you know, playing around out in the shop trying to come up with a product that's useful, this should get the job done. That being said, don't feel like you have to have everything perfect just to start the project. What we did was we got the sketch down, and we started designing it, started doing the plan session that you saw there, talked it out, looked at a few things, and this evolved over time. I even started wiring it before we got to this final version. So there's a whole lot of things that go on here that don't be afraid to change something as you learn more, or you look at it in a different light on a different day. This didn't all happen one day. So don't be afraid to change what you worked on. So I just thought that might be a fun recap for this first video in the series. Check out the build part, or take a look at the test section as well. We'll create a playlist so you can watch all 3. I realize it's a lot of content, and you know, it might take a little bit of a time investment to watch through it all, but hopefully it'll be interesting. Hopefully it'll inspire some people. You know, designing things isn't overly complex. It starts to look it after a while, but really the fundamentals are all still this. And then it builds upon that. It just kind of gets refined and cleaned up. You know, we go from the idea of a basic inverter in a box, and you know, we end up with protection fuses and diodes to help protect the switches, and cooling fans, and all that other stuff. It just got built upon from there. So hopefully this is helpful for people. Hopefully you enjoy the series. Thanks for watching. Have a great day.